Look up at the night sky, and you're seeing an ancient light show, a tapestry of stars that has captivated humanity for millennia. For most of our history, the cosmos felt like a beautiful but distant painting, static and eternal. But that picture was an illusion. Over just the past century, our understanding has been utterly transformed. We now know the universe is not a serene, unchanging void, but a dynamic, explosive, and deeply mysterious arena where reality itself is stranger than fiction. It's a story still being written, and every new discovery rips up the old script, forcing us to see our place in the cosmos in a completely new light. This journey of cosmic revelation is what we're exploring today, a countdown of the 25 space discoveries that didn't just add to our knowledge, but fundamentally rewired our perception of everything. From the fiery birth of the universe to the shadowy realms where space and time break down, these are the findings that changed us, that answered ancient questions only to pose even deeper, more thrilling ones. Think of the awe our ancestors felt gazing at the constellations. We now get to experience that same sense of wonder, but magnified by the staggering truth science has unveiled. The universe is not what we thought it was. It's wilder, more violent, more beautiful, and infinitely more complex. And every one of these discoveries is a chapter in the greatest story ever told. The story of how we, a species on a tiny rock orbiting an average star, began to decode the grandest mysteries of existence. We're about to travel from the very beginning of time to the edge of our current understanding, visiting cosmic landmarks that have reshaped science and philosophy. We'll encounter echoes of the creation event itself, ghostly particles that pass through our bodies by the billions, and monsters so dense they trap light itself. This isn't just a list of facts, it's an invitation to witness the key moments when humanity's cosmic perspective shifted forever. So let's begin this journey together, back to the very first moments, to the discovery that provided the origin story for everything we see. And that origin story begins with a discovery that fundamentally rewrote our cosmic history. In the early 1960s, two radio astronomers, Arno Penzias and Robert Wilson, were working with a massive, ultra-sensitive horn antenna at Bell Labs in New Jersey. They were plagued by a persistent, faint hiss, a uniform noise that came from every direction in the sky and wouldn't go away no matter what they did. They even famously cleaned out pigeon droppings from the antenna, convinced the mess was the source, but the mysterious static remained. This annoying background hum, which they couldn't eliminate, turned out to be the most important noise in the history of science. It was the cosmic microwave background radiation, the cool, faded afterglow of the Big Bang itself. This was the first solid, observable evidence that our universe wasn't eternal and static, but had a definite, explosive beginning. Think of the universe not as an infinite, unchanging stage, but as a dynamic, expanding entity. When it was young, it was an unimaginably hot, dense fireball. As it expanded and cooled over billions of years, that primordial light lost energy, stretching from visible wavelengths all the way down to the microwave region of the spectrum. What Penzias and Wilson had accidentally stumbled upon was the remnant heat from that initial explosion, now cooled to just about 2.7 degrees above absolute zero, bathing the entire cosmos. This discovery was the final, crucial piece of evidence that transformed the Big Bang from a speculative theory into the foundational model of modern cosmology. It meant the universe had a birthday. It meant that space and time themselves are not a fixed backdrop but were created in that initial event. Every galaxy, every star, every atom in our bodies originated from that searing hot beginning. This single finding answered an ancient question about our origins while posing a cascade of new ones. What triggered the Big Bang? What, if anything, came before it? The universe was no longer a serene, eternal void. It was a vibrant, evolving story with a starting gun whose echo we can still hear today. But if the universe began with a bang, what happened next? The next monumental discovery gave us the answer, and it completely overturned one of humanity's most deeply held beliefs about the cosmos. For centuries, the prevailing view, championed by thinkers like Aristotle and even Einstein initially, was of a static, eternal, and unchanging universe. The Milky Way was thought to be the entirety of creation, an island of stars fixed in an infinite, empty space. Then, in the 1920s, an astronomer named Edwin Hubble, using the powerful new 100-inch Hooker telescope at Mount Wilson Observatory, made a series of observations that would tear this static picture to shreds. He was studying faint, fuzzy patches of light then known as nebulae. Through meticulous work, he confirmed that these were not clouds of gas within our own galaxy, but entire other galaxies, island universes millions of light years away. This alone was a staggering blow to our cosmic ego, revealing that our Milky Way was just one of countless galaxies adrift in a vast ocean of space. But Hubble didn't stop there. By analyzing the light from these galaxies, he noticed something even more profound. The light from almost all of them was shifted toward the red end of the spectrum. This redshift wasn't a random effect, it had a clear and shocking pattern. The farther away a galaxy was, the greater its light was redshifted. In the same way, the pitch of a siren drops as a police car speeds away from you, a phenomenon known as the Doppler effect. This redshift meant the galaxies were all rushing away from us, and the most distant galaxies were fleeing the fastest. This relationship, now enshrined as Hubble's law, painted a breathtaking new picture. The entire universe is expanding. It's not that galaxies are simply moving through a pre-existing space. Space itself is stretching, carrying the galaxies along with it, like raisins in a rising loaf of bread. Imagine dots on the surface of an inflating balloon. As the balloon expands, every dot moves away from every other dot. There is no center to the expansion on the balloon's surface, and likewise, there is no center to the universe's expansion. We are not at a privileged central point. From any galaxy, every other galaxy would appear to be moving away. This single observation fundamentally changed our scale of reality. The universe was not just vast, it was dynamically growing, evolving from a much denser, hotter state. This expansion, when run backwards in time, logically points to a moment when all matter and energy were compressed into an infinitesimal point, the singular beginning we now call the Big Bang. Hubble's discovery didn't just give us more space, it gave us a story, a cosmic narrative with a past, a present, and a future. It transformed the universe from a static stage into a dynamic, unfolding drama, setting the scene for everything that was to come. Hubble's revelation of an expanding universe set the stage for a cosmic story of incredible scale and energy, but it also set the stage for a mystery that would prove even more profound. Because as astronomers began to map the universe in greater detail, they realized that the things we can see, the stars, the galaxies, the glowing gas, tell only a tiny fraction of the story. The real narrative is dominated by something we cannot see at all. Our next discovery is not about light, but about the haunting gravitational footprint of an invisible component that permeates the cosmos. The story of dark matter begins not with a eureka, a moment, but with a puzzle. In the 1930s, a brilliant and often controversial astronomer named Fritz Zwicky was studying the Coma Cluster, a massive collection of over 1,000 galaxies bound together by gravity. By measuring how fast these individual galaxies were whizzing around within the cluster, he could calculate the cluster's total mass, the glue holding it all together. What he found was baffling. The visible mass of all those stars and nebulae was far, far too small to generate enough gravity to keep the cluster from flying apart. The galaxies were moving so quickly that they should have long since escaped their gravitational bonds and scattered into the void. Zwicky proposed there must be some form of Dunkelmaterei, or dark matter, providing the missing gravitational pull. His idea was so radical and his personality so abrasive that it was largely dismissed for decades. It took another 40 years and the meticulous work of astronomer Vera Rubin to bring the mystery of dark matter to the forefront of science. Rubin was studying the rotation of spiral galaxies. According to the laws of gravity as we understand them, stars on the outer edges of a galaxy, far from the bright, massive core, should orbit much more slowly than those near the center. Think of our own solar system. Pluto, way out on the fringe, moves at a snail's pace compared to Mercury, which whips around the sun. But when Rubin and her colleague Kent Ford measured the velocities of stars in the Andromeda Galaxy and others, they found something astonishing. The stars in the outer reaches were orbiting just as fast as those near the center. The entire galaxy was rotating as if it were a solid disk. This was impossible unless the galaxy was embedded within a gigantic, massive halo of some unseen material, a halo that extended far beyond the visible edge of the galaxy itself. This invisible substance wasn't emitting or absorbing light. It was only making its presence known through its immense gravitational influence. This was the clinching evidence for dark matter. We now understand that this mysterious substance makes up roughly 27% of the entire mass-energy content of the universe, while the ordinary matter that makes up planets, stars, and us accounts for less than 5%. Dark matter is the cosmic scaffolding. Its gravitational wells pulled together the primordial gas that formed the first galaxies, and its invisible tendrils weave the large-scale structure of the cosmos, determining where galaxies form and how they cluster together. We know it's there because without its gravitational grip, galaxies would fly apart and galaxy clusters would never have formed. Yet, after decades of searching, we still don't know what it is. It's not made of atoms or any known particles. It could be a new, exotic particle that interacts only feebly with normal matter, or it could point to a need to revise our fundamental understanding of gravity itself. The discovery of dark matter was a monumental humbling. It revealed that the universe we see is just the visible frosting on a vast, invisible cake, forcing us to accept that most of the cosmos is made of something entirely foreign to our experience. Just when we thought we had the universe's grand story figured out, a story that began with a bang and was set to end either in a fiery crunch or a slow, cold fade, along came a discovery so shocking it turned cosmology on its head. We had all accepted the narrative of a cosmos expanding from its initial explosion, with the collective gravity of all matter, both seen and unseen, steadily applying the brakes, slowing down the great cosmic getaway. But in 1998, two independent teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were using distant stellar explosions to measure this expected cosmic slowdown with unprecedented precision. They were observing a specific type of supernova known as a Type 1a, which acts as a standard candle. Because these supernovae always explode with roughly the same intrinsic brightness, astronomers can determine their true distance by then measuring how much their light is stretched or redshifted by the expansion of the universe. They can plot how fast the universe was expanding at different points in its history. The expectation was clear. The light from the most ancient, farthest-flung supernova would show that the expansion was much more rapid in the early universe, confirming that gravity had been steadily putting on the brakes ever since. But the data told a completely different and frankly unbelievable story. The distant supernovae were fainter than they should have been. This meant they were farther away than anyone had predicted. The only possible explanation was that the expansion of the universe wasn't slowing down at all. In fact, over the last several billion years, it has been speeding up. The cosmos isn't just coasting apart. Some mysterious repulsive force is actively pushing galaxies away from each other at an ever-increasing rate. This was the discovery of the accelerating universe, a finding so paradigm-shattering that it earned the teams the Nobel Prize in Physics in 2011. This acceleration is driven by something we call dark energy, a term that hides our profound ignorance behind a simple label. We don't know what it is, but we know what it does. It counteracts gravity. While gravity pulls matter together, dark energy works to push it apart on the largest scales. And it's not a minor player. Current measurements indicate that dark energy constitutes about 68% of the entire mass energy content of the universe. Think about that for a moment. The stars, planets, and galaxies we see and romanticize, that's less than 5%. The mysterious dark matter that holds galaxies together. That's about 27%. The dominant force, the one dictating the ultimate fate of everything, is this completely unknown dark energy. It's as if we spent centuries meticulously studying the characters, settings, and plot of a great novel, only to suddenly realize that the story's outcome is actually being controlled by an invisible, omnipresent force we never knew was there. This discovery radically altered our cosmic forecast. Instead of a big crunch where gravity eventually pulls everything back together, or a heat death where expansion slowly grinds to a halt, the universe now seems headed for a big rip scenario, where the accelerated expansion becomes so powerful over trillions of years that it tears apart galaxies, then solar systems, then stars and planets, and finally even atoms themselves. Dark energy is the central character in the final chapter of our universe, and we are only just beginning to understand its opening lines. The cosmic microwave background, that faint hiss discovered by Penzias and Wilson, was far more than just a uniform blanket of radiation. It was a celestial fossil, and reading its intricate details would require tools far beyond a simple radio antenna. This is where our story leaps from a foundational discovery to a detailed cosmic biography. In the 1990s, NASA Cosmic Background Explorer, or COBE satellite, was launched with a singular, profound mission: to measure the CMB with a precision never before possible. What COBE found was breathtaking. First, it confirmed with stunning accuracy that the CMB had a perfect blackbody spectrum, the exact thermal signature predicted for the cooled remnant of a hot, dense Big Bang. It was as if we had found the fossilized bone of a dinosaur and then conducted a chemical analysis that perfectly matched our theoretical models of its biology. But COBE's second finding was even more revolutionary. It discovered that the CMB was not completely smooth. Imprinted across the entire sky were tiny, minuscule variations in temperature anisotropies, mere millionths of a degree different from one patch to the next. These weren't flaws, they were features. These tiny ripples were the seeds of all cosmic structure. They represented regions of slightly higher density in the infant universe, where gravity's relentless pull would, over hundreds of millions of years, draw in more and more matter, eventually forming the first galaxies, stars, and everything we see today. The universe was no longer just a smooth, expanding fireball. It was a canvas with a specific, imprinted pattern that destined it to become the web of galaxies we observe. COBE had given us the universe's baby picture, and it was a portrait of incredible potential. This work was taken to an entirely new level by the European Space Agency's Planck mission, launched in 2009. Planck was like giving the entire field of cosmology a pair of glasses with a prescription 10 times stronger. It mapped the CMB with such exquisite sensitivity that it turned those initial blurry ripples seen by COBE into a high-definition map of the primordial universe. By analyzing the precise size and distribution of these hot and cold spots, scientists could answer fundamental questions with staggering accuracy. The geometry of the universe, for instance. Einstein's theory of general relativity tells us that mass and energy curve spacetime. The amount of total matter and energy in the cosmos should therefore dictate its overall shape, whether it is positively curved like a sphere, negatively curved like a saddle, or flat like a sheet of paper. The pattern of the CMB fluctuations revealed the answer with definitive clarity. Our universe is geometrically flat to within a razor-thin margin of error. This flatness, in turn, confirmed the existence of dark energy, as the total amount of normal and dark matter alone is insufficient to create a flat universe. Planck's data allowed us to take a cosmic census of unprecedented precision, telling us that the universe is 13.8 billion years old and that ordinary matter, the atoms in our bodies and in every star, makes up just under 5% of the total content. Dark matter comprises about 27%, and the mysterious dark energy driving the acceleration makes up the remaining 68%. These numbers are not rough estimates, they are etched into the subtle patterns of the CMB, a cosmic barcode we have learned to scan. This ancient light is therefore far more than a simple relic. It is the most authoritative document we possess about the origins, composition, and ultimate fate of everything that exists. Just as we were coming to terms with a universe dominated by invisible forces and an accelerating expansion, a discovery was made much closer to home in a cosmic sense that profoundly reshaped our view of our own place in the grand scheme. For all of human history, we only knew of planets orbiting our own sun. Our solar system was the singular model, the only example we had of how a star and its family of worlds could be arranged. We wondered if other stars had planets of their own, but for centuries it remained pure speculation, the stuff of science fiction. That all changed in October 1995 when two Swiss astronomers, Michel Mayor and Didier Queloz, made an announcement that sent shockwaves through the scientific community. Using the Haute Provost Observatory in France, they had found a planet orbiting a star called 51 Pegasi, a sun-like star about 50 light-years away. This world, named 51 Pegasi b, was the very first confirmed exoplanet ever discovered around a main sequence star like our own. The method they used was brilliantly indirect, relying on the subtle gravitational dance between a star and its orbiting planet. You see, a planet doesn't actually orbit a stationary star. Instead, both the star and the planet orbit a common center of mass. Since the star is vastly more massive, this center of mass lies very close to or even inside the star itself, causing the star to wobble ever so slightly in place. As the star wobbles toward us, the light waves we receive from it are compressed, shifting them slightly toward the blue end of the spectrum. As it wobbles away, the light waves are stretched, shifting them toward the red. By meticulously measuring these tiny, periodic shifts in the star's spectral lines, a technique known as the radial velocity method, Mayor and Queloz detected the invisible presence of a planet tugging on its sun. But the planet they found was utterly bizarre, defying all our expectations based on our own solar system. 51 Pegasi b was a gas giant, roughly half the mass of Jupiter, but it was orbiting impossibly close to its star, so close that its year lasted only about 4 Earth days. This meant the planet was blisteringly hot, a type of world we now call a hot Jupiter. Its existence shattered the paradigm of our solar system, where small, rocky worlds orbit close to the star and gas giants reign in the cold outer reaches. It proved that planetary systems could form in configurations wildly different from our own. This single discovery opened the floodgates. Soon after, another technique, the transit method, became a powerhouse of exoplanet detection. This involves monitoring the brightness of a star over time, watching for a tiny, periodic dip that occurs when a planet passes directly in front of it, blocking a small fraction of its light. This method, championed by space telescopes like NASA Kepler, doesn't just tell us a planet is there. It can reveal the planet's size and even allow us to analyze the chemical composition of its atmosphere by studying the starlight that filters through it. The combined power of these methods has revealed a cosmos teeming with planets. We have now confirmed the existence of over 5,000 exoplanets, with thousands more candidates awaiting verification. We've found planetary systems with multiple worlds packed into orbits smaller than Mercury's. We've discovered super-Earths and mini-Neptune's planetary types that don't even exist in our own solar system. We've found planets orbiting binary stars, just like the fictional Tatooine from Star Wars, and rogue planets that have been ejected from their systems, drifting alone through the cold darkness of interstellar space. This staggering diversity has completely transformed one of humanity's oldest questions. For millennia, we looked up at the stars and wondered, are we alone? The discovery of exoplanets has fundamentally reframed that question. We now know that planets are not rare cosmic accidents. They are a common, even universal, byproduct of star formation. With hundreds of billions of stars in our galaxy, the number of potential worlds is almost incomprehensible. The question is no longer if other planets exist, but where life might have taken hold. The search has shifted from finding planets to finding planets that are Earth-like, orbiting within their star's habitable zone, that Goldilocks region where temperatures are just right for liquid water to exist on the surface. Every new exoplanet discovered is a data point in a grand statistical exercise, teaching us not just about other worlds, but about the formation and uniqueness of our own pale blue dot. While the discovery of exoplanets revealed a universe teeming with worlds, another, even more extreme prediction of Einstein's theory was waiting to be confirmed: objects so bizarre and powerful that they warp the very fabric of reality. Our journey now takes us to the edge of spacetime itself, to the discovery of black holes. The story begins not with an observation, but with a mathematical inevitability. Just a few months after Albert Einstein published his theory of general relativity in 1915, the German physicist Karl Schwarzschild found a solution to its incredibly complex equations. His solution described a point of infinite density, a singularity surrounded by a spherical boundary called the event horizon. Once anything, matter, light, even information itself crosses this horizon, it can never return. The escape velocity exceeds the speed of light. It is a point of no return. Einstein himself was skeptical, believing such objects were merely mathematical curiosities too strange to actually exist in nature. For decades, black holes remained in the realm of pure theory. The first major breakthrough came from the death of massive stars. When a star many times more massive than our Sun exhausts its nuclear fuel, its core collapses catastrophically under its own immense gravity. For the most massive stars, no known force in the universe is strong enough to halt this collapse. It continues until all the star's mass is crushed into an infinitesimal point, creating a stellar mass black hole. The first strong candidate for such an object was discovered in the constellation Cygnus in 1971. Astronomers detected a powerful, flickering source of X-rays which they named Cygnus X1. This intense radiation wasn't coming from the black hole itself, since no light can escape it, but from its immediate environment. Cygnus X1 is part of a binary system, orbiting a massive blue supergiant star. The black hole's tremendous gravity is constantly pulling gas away from its companion star. This stolen gas doesn't fall straight in. Instead, it forms a vast, hot, swirling disk around the black hole called an accretion disk. As the gas spirals inward at nearly the speed of light, it is compressed and heated to millions of degrees, causing it to glow brilliantly in X-rays. By carefully measuring the orbit of the visible star, astronomers could calculate the mass of its invisible companion. The result was astounding: an object with about 15 times the mass of our Sun, all packed into a region of space so small it could only be one thing: a black hole. This was the first compelling observational evidence that these gravitational monsters were not just theoretical phantoms but real, physical objects in our cosmos. But the story of black holes gets even more incredible. While stellar mass black holes form from dying stars, astronomers began to find evidence for behemoths of an entirely different scale lurking at the very centers of galaxies, including our own. These are supermassive black holes with masses millions or even billions of times that of our Sun. The evidence for the one at the heart of our Milky Way, known as Sagittarius, a star built up over decades. By meticulously tracking the orbits of individual stars very close to the galactic center, astronomers could watch them whip around an invisible focal point at breathtaking speeds, some completing their orbits in just a few years. Using the laws of gravity, scientists calculated that the only object that could hold these stars in such frenzied orbits was a supermassive black hole with a mass equivalent to about 4 million suns. This discovery confirmed that black holes are not just stellar oddities. They are fundamental architects of galactic structure, their immense gravity shaping the formation and evolution of the galaxies they inhabit. The ultimate confirmation, the moment black holes transitioned from inferred objects to visual reality, came on April 10, 2019. The Event Horizon Telescope Collaboration, a global network of radio telescopes working in unison to create an Earth-sized virtual observatory, unveiled the first ever direct image of a black hole. The target was the supermassive black hole at the center of the galaxy M87, a colossus weighing in at 6.5 billion solar masses. The image did not show the black hole itself, as that is impossible. Instead, it revealed the black hole's dark shadow, the absence of light within its event horizon silhouetted against the brilliant, swirling glow of its superheated accretion disk. This iconic orange ring was a perfect match for predictions based on general relativity, showing us the violent environment where gravity is so intense that it bends light itself into a circular path. This image was more than just a spectacular picture. It was a direct test of our understanding of physics under the most extreme conditions imaginable. The discovery and confirmation of black holes have fundamentally revolutionized our understanding of gravity and spacetime. They are the ultimate laboratories for testing the limits of Einstein's theory and for probing the mysterious interface between general relativity and quantum mechanics. They have shown us that space and time are not a fixed stage, but a dynamic, malleable fabric that can be stretched, twisted, and even torn. From a curious mathematical solution to a cosmic reality, black holes stand as one of the most profound and awe-inspiring discoveries in our quest to understand the universe. While black holes revealed the extremes of gravity through their visible effects on matter and light, the universe had another, even more subtle way of communicating these violent events, one that required us to learn to listen to the very fabric of reality. For a century, ever since Einstein published his theory of general relativity, scientists had speculated about the existence of gravitational waves. The theory proposed that massive, accelerating objects should create ripples in the very fabric of spacetime itself, much like a spinning bowling ball would create waves on the surface of a taut trampoline. These ripples would propagate outward at the speed of light, stretching and compressing everything in their path by an almost infinitesimally small amount. Einstein himself was unsure if we would ever be able to detect something so faint, and for decades these waves remained a purely theoretical concept. The hunt to find them became one of the greatest technological challenges in the history of science. The breakthrough came on September 14, 2015, at the twin observatories of the Laser Interferometer Gravitational Wave Observatory, or LIGO. Each LIGO facility is an L-shaped instrument with arms 4 kilometers long, housed in a near-perfect vacuum. Inside, powerful lasers are split and sent racing down each arm, bouncing off exquisitely polished mirrors to be recombined. In a perfectly still universe, the light waves returning from each arm would cancel each other out, resulting in no signal. But if a gravitational wave passes through the Earth, it would momentarily distort space itself, making one arm infinitesimally longer and the other shorter, disrupting the laser light's perfect cancellation and creating a detectable flicker. The sensitivity required is almost beyond belief. LIGO is designed to measure a change in length 10,000 times smaller than the diameter of a proton. On that morning in 2015, both LIGO detectors, located thousands of miles apart in Louisiana and Washington state, registered an identical, unmistakable signal. The data trace showed a characteristic chirp, a rapid increase in the frequency and amplitude of the waves that lasted for just 0.2 of a second. When scientists converted this signal into sound, they heard the cosmic crescendo of two massive black holes, one about 36 times the mass of the Sun and the other 29, spiraling toward each other in a final, fatal dance. In the last frantic moments before they merged, they whipped around each other hundreds of times per second, pumping immense energy into the space-time around them, sending out these shudders that traveled across the cosmos for 1.3 billion years before finally reaching Earth. The merger created a single, more massive black hole, and in that instant, a quantity of mass roughly 3 times that of our Sun was converted directly into pure energy in the form of gravitational waves, an outburst of power that briefly outshone every star in the observable universe combined. This single detection was a triumph on multiple levels. It provided the first direct, unequivocal proof that black holes can exist in binary pairs and merge, a phenomenon that was only theoretical before. More fundamentally, it confirmed a key prediction of Einstein's general relativity a full century after he proposed it, showing that space-time is indeed a dynamic, flexible medium. But perhaps the most revolutionary aspect was what it meant for astronomy itself. For all of human history, we have studied the universe by observing light, from visible waves to radio, X-rays, and gamma rays. Gravitational waves are an entirely different cosmic messenger. They are not light, they are vibrations of space itself. This discovery flung open an entirely new window on the universe, allowing us to hear the cosmos for the very first time. Where traditional telescopes are blind, gravitational wave observatories can perceive the most cataclysmic events, like the collisions of black holes and neutron stars, which often occur without emitting any light at all. This new sense has given us access to a hidden symphony of the universe, a chorus of ripples from the most violent and energetic processes imaginable. It marks the dawn of a new era in astronomy, where we are no longer just silent observers of a cosmic light show, but active listeners to the very heartbeat of space-time. But what is it that actually gives substance to the universe? We've talked about cosmic expansion, dark matter, and dark energy, but what about the very stuff that makes up the world we can touch and see? This brings us to one of the most profound discoveries in particle physics, a finding that completes our picture of the early universe on its very smallest scales. In July 2012, scientists at CERN, the European Organization for Nuclear Research, announced they had found the Higgs boson. This was the culmination of a decades-long hunt, involving thousands of researchers and the most complex machine ever built, the Large Hadron Collider. But the importance of this discovery goes far beyond a single particle. It answers a fundamental question about the nature of reality itself. Why does anything have mass? To understand this, we need to think not just about particles, but about invisible fields that fill all of space. You're already familiar with one field, the magnetic field. You can't see it, but you know it's there because it can push on a magnet. The universe is permeated by such fields, and the most important one for giving things mass is the Higgs field. Imagine the entire cosmos is filled with an invisible, treacly substance, a cosmic molasses. As fundamental particles move through this field, they interact with it. Particles that interact a lot, like quarks and electrons, get bogged down, and this resistance to motion is what we experience as mass. A particle that didn't interact with the Higgs field at all, like the photon, would have no mass and must always travel at the speed of light. The Higgs boson is the physical manifestation of this field. It's the smallest possible ripple or excitation in the Higgs field, and detecting it was the ultimate proof that the field is real. Without this mechanism, the universe would be a fundamentally different and far less interesting place. Right after the Big Bang, in the searing heat of the first fractions of a second, the Higgs field was turned off. In that primordial symmetry, all particles were massless, zipping around at the speed of light. The universe was a formless, energetic soup. but as the cosmos expanded and cooled, in a pivotal moment about a billionth of a second after the beginning, the Higgs field switched on. This event, known as the electroweak phase transition, broke the symmetry of the fundamental forces and endowed certain particles with mass. This was a cosmic milestone of unimaginable importance. Suddenly, particles that were once racing around at light speed began to slow down. This slowdown was crucial because it allowed those particles to clump together. If electrons remained massless, they could not be captured by protons to form stable atoms. There would be no atoms, no molecules, no stars, no planets, and no us. The Higgs mechanism provided the necessary friction for the universe to congeal from a hot, featureless plasma into the structured cosmos we see today. It is the reason there is something rather than nothing in a tangible, substantive form. Finding the Higgs boson was therefore not just about checking a box in the standard model of particle physics. It was about confirming the origin of mass, the very property that allows matter to assemble and build a complex universe. It connects the infinitesimally small world of quantum particles to the grand cosmic narrative, showing us that the laws governing the tiniest building blocks are directly responsible for the existence of everything we hold vast. Just as the universe was revealing its most violent collisions through gravitational waves, another discovery decades earlier had already given us a front-row seat to one of the most exotic and precise objects in the cosmos. The year was 1967, and a young graduate student at the University of Cambridge named Jocelyn Bell Burnell was meticulously analyzing data from a new radio telescope she had helped build. The instrument was designed to study quasars, but Bell noticed something peculiar in the endless reams of chart paper, a faint, repeating signal that appeared as a series of sharp, precisely spaced pulses. These scruff signals, as she called them, were unlike anything seen before. They arrived with such clockwork regularity, every 1.337 seconds, that the possibility of an artificial source was seriously considered. In a moment of scientific humor mixed with genuine bewilderment, the source was half-jokingly labeled LGM-1 for Little Green Men. It was a thrilling and disquieting thought. Had they truly stumbled upon a beacon from an advanced extraterrestrial civilization? Of course, the truth, once uncovered, was almost as astounding. What Bell and her supervisor, Anthony Hewish, had discovered was not an alien message, but the first known pulsar. A pulsar is a rapidly spinning neutron star, the incredibly dense, city-sized corpse of a massive star that went supernova. When such a star explodes, its core collapses under immense gravity, crushing protons and electrons together to form neutrons. The result is an object so dense that a single sugar cube-sized piece of it would weigh as much as a mountain here on Earth. This stellar cinder retains the original star's angular momentum, but because it has collapsed to such a small size, it spins incredibly fast, just like an ice skater pulling in their arms to accelerate a spin. The Crab Nebula pulsar, for instance, the remnant of a supernova observed by Chinese astronomers in 1054, spins 30 times every single second. But how does this create the pulse? Neutron stars possess immensely powerful magnetic fields, trillions of times stronger than Earth's. These fields funnel intense beams of radiation radio waves, light, X-rays, out from the star's magnetic poles. If these magnetic poles are misaligned with the star's rotational axis, then as the star spins, these lighthouse-like beams sweep across the cosmos. From our vantage point on Earth, every time one of these beams flashes across our telescopes, we detect a pulse. The incredible regularity of these pulses comes from the neutron star's phenomenal rotational stability. They are the most accurate natural clocks in the universe, rivaling even our best atomic clocks. The discovery of pulsars was a watershed moment. It provided the first direct observational evidence for the existence of neutron stars, which until then had been only a theoretical possibility. It gave us a vivid new understanding of stellar death, showing that a supernova isn't just an end, but a transformative event that can create these bizarre, ultra-dense objects. But the utility of pulsars went far beyond just confirming their own existence. Because their pulses are so regular, any tiny deviation in their timing can be measured with extraordinary precision. This makes them exquisite tools for testing the very fabric of space-time. For example, the first indirect evidence for gravitational waves came from studying a very special system, a binary pulsar. In 1974, astronomers discovered a pulsar orbiting another neutron star. By meticulously timing the pulses from one of them, Russell Hulse and Joseph Taylor could map its orbit with incredible detail. They found that the orbit was gradually shrinking, meaning the two stars were slowly spiraling inward toward each other. The rate at which they were losing orbital energy perfectly matched the predictions of Einstein's general relativity for energy being carried away from the system in the form of gravitational waves. This was a monumental confirmation of a key aspect of Einstein's theory, earning Hulse and Taylor the Nobel Prize and paving the way for the direct detection by LIGO decades later. Today, astronomers use networks of pulsars across the galaxy in an ambitious endeavor called pulsar timing arrays, attempting to detect the faint, background hum of gravitational waves from supermassive black hole binaries merging in the hearts of distant galaxies. Pulsars have even been used as navigational beacons for proposed interstellar spacecraft, their predictable signals acting as cosmic GPS points. From a mysterious scruff on a chart to a fundamental tool for probing gravity and spacetime, the discovery of pulsars opened a new window into the most extreme physical regimes in the universe, showing us that even in stellar death, there can be a strange and beautiful order. Just as pulsars revealed the precise ticking clocks of dead stars, the 1960s unveiled an entirely different kind of celestial phenomenon, one that seemed to defy all logic. Astronomers surveying the sky with radio telescopes began to pinpoint strange, powerful sources of radio waves that had no visible counterpart. When they finally managed to link these radio sources to what looked like faint blue stars through optical telescopes, they assumed they had found oddballs within our own galaxy. But when they analyzed the light from these stars, they got the shock of their lives. The spectral lines were dramatically shifted toward the red end of the spectrum, a redshift so immense it meant these objects weren't stars at all. They were billions of light-years away, farther than most known galaxies. This presented an immediate and profound paradox. To appear as bright as they did from such cosmic distances, these objects had to be unleashing almost unimaginable amounts of energy. The first one identified, known as 3C273, was calculated to be shining with the luminosity of 1,000 Milky Way galaxies, all packed into a region of space not much larger than our solar system. How could something so small produce so much light? They were dubbed quasi-stellar radio sources, a name soon shortened to quasars, and their discovery sent astrophysicists scrambling for an explanation. The only conceivable engine powerful enough to fuel such a beacon was a supermassive black hole, millions or even billions of times the mass of our Sun, lurking at the quasar's heart. But unlike the quiet giant at the center of our Milky Way, these black holes were in an intensely active phase. Imagine a gravitational maelstrom of unbelievable scale. Vast clouds of gas, dust, and even entire stars are caught in the black hole's irresistible pull, forming a searingly hot, rapidly spinning accretion disk. As this material spirals inward at nearly the speed of light, it is compressed and heated to temperatures of millions of degrees, converting gravitational potential energy into a torrent of radiation across the entire electromagnetic spectrum before it finally crosses the event horizon and vanishes. This process of accretion is staggeringly efficient, converting up to 40% of the infalling mass directly into energy according to Einstein's famous equation, E equals mc squared. For comparison, the nuclear fusion that powers stars is only about 0.7% efficient. A quasar is, in essence, a black hole operating at maximum throttle, turning matter into pure light on an industrial scale. The prodigious energy output of quasars did more than just solve an astronomical puzzle. It fundamentally changed our view of cosmic history. Because light takes time to travel, looking out into the distant universe is the same as looking back in time. The fact that we see so many quasars at colossal distances means they were far more common in the early universe, roughly 10 billion years ago. This revealed a pivotal epoch that was infinitely more violent and chaotic than the relatively quiet cosmos we inhabit today. In that formative era, galaxies were young, gas was abundant, and supermassive black holes at their centers were feasting on this rich supply of fuel, blazing forth as quasars and fundamentally shaping the evolution of the galaxies they lived in. Their intense radiation and powerful jets of material streaming away at near light speed could heat surrounding gas, regulate star formation, and literally blast away the raw materials for future stars, acting as a galactic-scale thermostat. The age of quasars was a time of cosmic construction and demolition, where these brilliant beacons were not merely strange outliers, but central players in the story of how galaxies like our own came to be. Shifting our gaze from the deepest cosmos to our own celestial backyard, we find a tempest of such scale and longevity that it challenges our very understanding of weather itself. For more than 350 years, a colossal, swirling vortex has been churning in the atmosphere of Jupiter, a storm so vast it could swallow our entire planet whole. This is the Great Red Spot, a planetary marvel first definitively observed in the 1600s by astronomers like Giovanni Cassini, though it may have been raging for far longer. It is not a static feature but a dynamic hurricane-like storm, an anticyclonic monster spinning counterclockwise in Jupiter's southern hemisphere. Think of the most powerful hurricane you can imagine, then magnify it beyond comprehension. The Great Red Spot is typically about 10,000 miles across, though it has been shrinking and changing shape over the decades. Winds at its outer edges scream at speeds exceeding 270 miles per hour, whipping around a center that is eerily calm, much like the eye of a terrestrial hurricane but on a godlike scale. What keeps this ancient storm going? On Earth, hurricanes are fueled by warm ocean water and quickly dissipate when they move over land or cooler waters. Jupiter, however, is a gas giant with no solid surface to disrupt the flow. The Great Red Spot is a self-sustaining atmospheric engine powered from above and below. Heat rising from Jupiter's immensely hot interior provides a constant source of energy, while the storm itself acts as a giant mixer, drawing in warmer gases from below and cooler gases from above, creating a continuous cycle of convection that has allowed it to outlive every civilization in human history. Its famous reddish color is thought to come from chemical compounds, perhaps complex hydrocarbons or phosphorus-bearing molecules, being dredged up from deeper layers of the atmosphere and altered by the sun's ultraviolet light, a cosmic cooking process we are still working to fully understand. The endurance of the Great Red Spot has provided a natural laboratory for studying fluid dynamics on a scale impossible to replicate on Earth. It has taught us about the stability of long-lived vortices and how such systems can maintain their identity while absorbing smaller storms and interacting with the chaotic jet streams that stripe the planet. By observing its behavior, scientists can test sophisticated computer models of atmospheric circulation, models that are crucial for understanding our own climate and the weather on other worlds. This single, persistent storm has fundamentally reshaped our view of gas giants. We now know they are not placid, featureless orbs but violently dynamic worlds, with atmospheres layered in complex bands of eastward and westward winds, peppered with storms of various sizes and lifetimes. The discovery of similar, though less permanent, features on Saturn and Neptune confirms that the principles at work in the Great Red Spot are universal. It is a stunning demonstration that the laws of physics can create phenomena of breathtaking beauty and fearsome power, a permanent monument to the turbulent nature of planetary formation that has watched over our solar system for centuries. For centuries, our solar system appeared to have a clear and well-defined edge, marked by the orbit of the most distant known planet. But as we peered deeper, we realized the planetary realm was not the end of the story. Far beyond the last gas giant lies a vast, frigid frontier, a cosmic deep freeze holding the frozen building blocks of our planetary system and rewriting the map of our celestial neighborhood. This discovery began with a mystery that has captivated humanity for millennia: comets. These spectacular visitors with their brilliant tails were long seen as omens, but with the dawn of modern astronomy, they became a profound puzzle. Where did they come from? Astronomers like Jan Ewart and Gerard Kuiper realized that comets falling into the inner solar system from random directions couldn't have been orbiting the Sun for billions of years. Their volatile ices would have long since been vaporized by solar radiation. There had to be a vast, distant reservoir, a storage locker for these icy remnants, kept in deep freeze until a gravitational nudge sent one falling sunward. This theoretical prediction led to our modern understanding of two distinct, immense structures that define the true outer limits of our solar system. The first to be observationally confirmed was the Kuiper belt. Think of it as a colossal, donut-shaped region of space, beginning just beyond the orbit of Neptune and extending outward for billions of miles. It's a cosmic junkyard filled with countless icy bodies, some small like dirty snowballs, others large enough to be considered dwarf planets. For decades, it remained a theoretical concept until the 1990s, when astronomers began discovering these distant, slow-moving objects. The most famous of these is, of course, Pluto. Once considered the ninth planet, the discovery of other large Kuiper belt objects like Eris, which is similar in size to Pluto, forced a dramatic reclassification. We came to understand that Pluto was not a solitary anomaly but the king of a vast population of icy worlds. This led the International Astronomical Union to create the new category of dwarf planet in 2006, a decision that was controversial but scientifically necessary. It reshaped our solar system's family portrait, showing us that instead of 9 planets, we have a dynamic system with rocky inner planets, gas giants, and a sprawling third zone of icy bodies. The New Horizons spacecraft's flyby of Pluto in 2015 brought this new world into stunning focus, revealing a complex, geologically active landscape with towering mountains of water ice and vast plains of frozen nitrogen, proving that even small, distant worlds can harbor surprising complexity. But the Kuiper belt is just the inner porch. Far, far beyond it, extending perhaps halfway to the next star, lies the Oort cloud. This is a theoretical sphere of trillions of icy objects, so distant that the Sun is just a bright star in their sky. We have never directly observed an object in the Oort cloud. Its existence is inferred from the trajectories of long-period comets. These comets, which take thousands or even millions of years to complete a single orbit, come from all directions, not just the flat plane of the solar system. This spherical distribution is the key evidence for the Oort cloud. It's thought to be a remnant of the solar system's formation, a shell of icy planetesimals that were scattered outward by the gravitational kicks of the young giant planets billions of years ago. These two reservoirs are more than just comet factories. They are pristine archives of the early solar system. The objects in the Kuiper belt and Oort cloud have been in a state of deep freeze since the planets first formed, preserving the original chemical and physical conditions of that nascent era. Every time a comet like Hale-Bopp or Neowise streaks through our inner solar system, it is delivering a sample of that primordial material, a messenger from the very dawn of our planetary system. Their study allows us to perform a kind of cosmic archaeology, unlocking the secrets of how our world and potentially others came to be. The discovery of these distant zones fundamentally expanded our sense of home. Our solar system is not merely a set of planets orbiting a star. It is a sprawling domain of influence with gravitational tentacles reaching nearly a light year into interstellar space. It revealed that the process of planet formation is a messy, violent affair that leaves behind a vast swath of debris, and it provided the missing link in the life cycle of comets, transforming them from mysterious apparitions into predictable, though still spectacular, members of our solar family. As we rewind the cosmic clock back to those first fleeting moments after the Big Bang, the standard model we've discussed runs into some serious trouble. It couldn't explain why the universe appears so remarkably uniform in every direction, or why the fabric of space itself appears so geometrically flat. To solve these profound puzzles, cosmologists had to propose an event even more dramatic than the Big Bang itself, a concept known as cosmic inflation. This theory suggests that in the very first fraction of a second, a minuscule patch of the infant universe underwent a staggering, exponential expansion, inflating from something trillions of times smaller than a proton to a size comparable to a grapefruit in less than a billionth of a billionth of a billionth of a second. This wasn't the steady, measured expansion we see today, governed by dark energy. This was a violent, hyper-driven stretching of spacetime itself, a period of faster-than-light growth that set the stage for everything to come. This incredible idea solved the horizon problem, which asks how regions of the universe on opposite sides of the sky could have the exact same temperature when there hasn't been enough time since the beginning for light or heat to travel between them. Without inflation, these regions should be completely disconnected, like two strangers in different countries independently deciding to wear the exact same outfit, a wild and unbelievable coincidence. Inflation fixes this by proposing that the entire observable universe was once a single, tiny, interconnected region that was heated to a uniform temperature before being blown up to cosmic proportions, preserving that original uniformity across the vast expanse we see today. It also explains the flatness problem. Why is the universe's geometry so perfectly balanced, so flat? Think of a balloon. When you inflate it to an enormous size, even a small, initially crumpled patch on its surface becomes smooth and flat from your perspective. In the same way, the inflationary expansion stretched the primordial universe so dramatically that any initial curvature was smoothed out, leaving behind the geometrically flat cosmos that the Planck satellite later confirmed with such precision. But perhaps the most profound gift of inflation was providing the origin story for all structure in the universe. According to the theory, this rapid expansion was driven by a mysterious energy field called the inflaton field. And like all quantum fields, it was subject to tiny, random fluctuations at the smallest scales. As the universe inflated at a breathtaking rate, these microscopic quantum jitters were stretched to astronomical sizes, frozen into the fabric of spacetime as minute differences in density. These tiny ripples in the primordial soup became the gravitational seeds for everything that followed. The slightly denser regions had a bit more gravitational pull, slowly attracting more and more matter over billions of years, eventually collapsing into the first galaxies, stars, and the vast cosmic web we observe today. The most compelling evidence for this incredible sequence of events is written in the cosmic microwave background. The tiny temperature variations that Cope and Planck so precisely mapped are a direct imprint of those initial quantum fluctuations magnified by inflation. They have exactly the pattern and distribution that the theory of inflation predicts, a statistical fingerprint that matches beautifully. Without this brief but monumental burst of growth, the universe might have remained a smooth, featureless, and lifeless plasma, with no planets, no stars, and no one to ponder its existence. Cosmic inflation provides the crucial prologue to the Big Bang story, explaining not just how the universe began, but how it got its spectacularly lumpy, structured, and habitable form. The hunt to measure the universe's expansion rate with this level of precision required more than just powerful telescopes. It demanded a specific kind of cosmic flare, a reliable beacon that could be seen across billions of light years. Astronomers found their perfect tool in a particular class of stellar cataclysm, the Type Ia supernova. These spectacular explosions are not born from the chaotic collapse of a single massive star. Instead, they arise in a binary system where a dense stellar corpse called a white dwarf, the Earth-sized core left behind by a sun-like star, is locked in a gravitational dance with a companion. The white dwarf, primarily composed of carbon and oxygen, is incredibly stable, supported against its own gravity by a quantum mechanical effect called electron degeneracy pressure. But stability turns to catastrophe if the white dwarf can steal enough matter from its partner. As it accretes gas, its mass slowly climbs toward a critical threshold known as the Chandrasekhar limit, about 1.4 times the mass of our Sun. At this precise point, the pressure and temperature in the white dwarf's core become so extreme that a runaway nuclear fusion reaction ignites, ripping the entire star apart in a titanic blast. Because this detonation always happens at almost exactly the same mass, the intrinsic brightness or luminosity of a Type Ia supernova is remarkably consistent. This consistency is what makes them phenomenal standard candles. Just as you can judge how far away a car is at night if you know the true brightness of its headlights, astronomers can measure the apparent faintness of a distant Type Ia supernova and calculate its precise distance. This is the first crucial part of the puzzle. The second part involves measuring how much the universe has stretched since the light from that supernova began its journey. This is where redshift comes in. As the universe expands, the wavelength of light traveling through it gets stretched along with the fabric of space itself. The farther the light has to travel, the more it is stretched, shifting its color toward the red end of the spectrum. By analyzing the spectrum of light from a supernova, astronomers can measure this redshift, which tells them how much the universe has expanded during the time the light was in transit. By the late 1990s, two independent teams, the Supernova Cosmology Project led by Saul Perlmutter and the High Z Supernova Search Team led by Brian Schmidt and Adam Rees, were engaged in a high-stakes race. They were using the world's most powerful telescopes to hunt for these distant supernovae, painstakingly comparing their observed brightness, which gave them the distance, with their measured redshift, which told them how much the universe had expanded. The universal expectation, grounded in the understanding that gravity should be slowing the cosmic expansion, was clear. The most distant supernova, those whose light was emitted billions of years ago, would appear brighter than expected. This would mean they were closer than predicted, indicating that the expansion was much faster in the past and has been decelerating ever since under gravity's pull. The data, however, told a completely different and mind-bending story. The high redshift ancient supernovae were consistently fainter than their redshifts indicated they should be. If they were fainter, they had to be farther away. The only possible explanation for them being so far away was that the expansion of the universe was not slowing down at all. In fact, over the last several billion years, it has been speeding up. Some mysterious repulsive force was actively working against gravity, pushing galaxies apart at an ever-increasing rate. The teams had independently and unequivocally discovered the accelerating universe. This conclusion was so radical that the researchers spent months checking and rechecking for potential errors. Perhaps intergalactic dust was dimming the light, or the ancient supernovae were inherently different from modern ones. But after exhaustive analysis, those possibilities were ruled out. The evidence was solid. The universe was not just expanding, it was in a state of runaway acceleration. This discovery was so profound it earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. The driver of this acceleration received a name that perfectly captures our current state of knowledge: dark energy. We call it dark because, like dark matter, it does not interact with light in any way we can detect. We call it energy because it seems to be a property of space itself, a constant energy density that permeates the vacuum of the cosmos. As the universe expands and new space is created, more of this dark energy appears, leading to a self-reinforcing cycle of acceleration. The simplest explanation, though by no means the only one, is that dark energy is the cosmological constant, a term Albert Einstein originally inserted into his equations of general relativity to achieve a static universe, which he later called his greatest blunder. It turns out he may have been right for the wrong reason. The cosmological constant represents a constant energy density of empty space, and its repulsive gravity is the leading candidate for what we now observe. The implications of this discovery are staggering. Dark energy is now understood to be the dominant component of the universe, making up about 68% of its total mass energy content. It dictates the ultimate fate of the cosmos, pointing toward a future where the acceleration continues unabated. Over trillions of years, this could lead to a big rip scenario where the expansion becomes so powerful that it tears apart galaxies, then solar systems, stars, planets, and finally even atoms and atomic nuclei themselves. The discovery of the accelerating universe via Type Ia supernova was a pivotal moment of cosmic humility. It showed us that the forces shaping reality on the largest scales are not only invisible, but are also completely unlike anything we experience in our local, gravity-dominated corner of the cosmos, presenting one of the most profound and pressing mysteries in all of modern science. Just as we were mapping the structure of the cosmos and the life cycles of stars, a completely different kind of signal began to arrive, a signal so powerful it temporarily blinded the very instruments designed to watch for nuclear explosions. In the late 1960s, the United States launched a series of top-secret military satellites known as the Vela Fleet. Their mission was to monitor the skies for gamma-ray flashes, the telltale signature of prohibited nuclear weapons tests in space. The satellites functioned perfectly, but they began picking up something entirely unexpected and baffling. They weren't detecting clandestine bomb tests from Earth. They were detecting colossal, random flashes of energy coming from deep space. These bursts of gamma rays, the most energetic form of light, would appear without warning from any direction, last for a few seconds, and then vanish forever. For years, this data was locked away in classified files, a cosmic mystery known only to a handful of defense analysts. Once the data was declassified and shared with the astronomical community in the 1970s, the true nature of the puzzle became clear, and the scientific scramble to explain these gamma-ray bursts began in earnest. The first major challenge was figuring out just how far away they were. Were they relatively local events within our own galaxy, or were they coming from the edge of the observable universe? The breakthrough came in the 1990s with the Italian-Dutch Beppo SAX satellite. This spacecraft had a unique ability. It could not only detect a gamma-ray burst, but also quickly pinpoint its location with enough accuracy for ground-based telescopes to swing into action and observe the fading afterglow in visible light, X-rays, and radio waves. When astronomers did this, they found something staggering. The afterglows were located in incredibly distant galaxies, billions of light-years away. For a flash of gamma rays to be visible from such a mind-boggling distance, the energy release had to be almost beyond comprehension. In just a few seconds, a single gamma-ray burst can outshine the combined light of every star in its entire host galaxy. In fact, for their brief duration, they are the most luminous events in the entire universe since the Big Bang itself. Concentrating more energy than our Sun will emit over its entire 10-billion-year lifetime. We now understand that these cosmic bombs come in two primary varieties, each with its own terrifying origin story. The longer bursts, lasting more than 2 seconds, are now linked to the death of the most massive stars in the universe. When a star dozens of times more massive than our Sun reaches the end of its life, it doesn't just go supernova in a conventional way. Its core collapses directly into a black hole, and in the process, it unleashes ultra-focused jets of material and radiation that scream outward at over 99.9% of the speed of light. If one of these incredibly powerful jets happens to be pointed directly at Earth, we see it as a long-duration gamma-ray burst, a final, brilliant beacon signaling the birth of a new black hole and the utter destruction of its parent star. The shorter bursts, lasting less than 2 seconds, have an equally violent origin. They are the result of two super-dense neutron stars spiraling together in a final, furious dance. As these city-sized stellar corpses, each more massive than our Sun, circle each other, they radiate away energy in the form of gravitational waves, inevitably drawing closer until they finally merge. This cataclysmic collision also creates a black hole almost instantly, and for a fraction of a second, blasts out those focused jets of gamma radiation. It was the detection of both gravitational waves and gamma rays from the same event in 2017 that confirmed this origin story beyond any doubt, marking a triumph of multi-messenger astronomy. But the importance of gamma-ray bursts goes far beyond their spectacular origins. Because they are so intensely bright, they act as cosmic lighthouses, their light piercing through the fog of the early universe. The most distant gamma-ray bursts we have detected let us study the conditions of the cosmos when it was only a few 100 million years old, a time when the first stars and galaxies were just beginning to form. By analyzing the way their light is absorbed by intervening gas clouds, we can take a chemical census of the primitive universe, tracing the creation of the first heavy elements. They are, in effect, fleeting probes that illuminate the dark, distant epochs that are otherwise nearly impossible to observe. From a classified anomaly on military satellites to recognized as the universe's ultimate heavy artillery, the discovery of gamma-ray bursts revealed a cosmos of unimaginable violence where the birth cries of black holes echo across billions of light years, offering us a fleeting, brilliant window into the most energetic and transformative event since the beginning of time. For much of human history, our cosmic address was a profound mystery. We lived inside the Milky Way, a pale, luminous band arching across the night sky, but its true shape and our place within it were completely unknown. The journey to map our galactic home is a story of slowly dethroning ourselves from a central position, a process that began in earnest with the work of an 18th century musician turned astronomer William Herschel. In the 1780s, Herschel undertook a monumental task. He would literally count the stars. With his sister Caroline as his invaluable assistant, he meticulously surveyed the heavens, assuming that the number of stars he could see in any given direction would reveal the shape of the star system. His method was simple in concept but laborious in practice. He pointed his telescope in hundreds of different directions and tallied the stars visible in its field of view. The resulting model, which he called a grindstone, depicted the Milky Way as a flattened, irregular disk with the Sun nestled near its center. It was a brilliant first attempt, a rough sketch of our island universe, but it was fundamentally flawed. Herschel had no way of knowing that vast clouds of interstellar dust, dark, obscuring veils, blocked the light from more distant stars, creating the illusion of boundaries where none truly existed and making some regions appear emptier than they were. This limitation meant his map was more a diagram of what we could see, rather than the true architecture of the galaxy itself. The pivotal breakthrough that would shatter the geocentric model of our galaxy came in the early 20th century, thanks to the work of an astronomer who dedicated her life to studying variable stars, Henrietta Swan Leavitt. While working at the Harvard College Observatory, Leavitt made a crucial discovery about a class of stars known as Cepheids variables. These stars pulsate rhythmically, growing brighter and dimmer over a regular period. Leavitt found that there was a direct relationship between a Cepheids pulsation period and its intrinsic brightness. A Cepheid that takes a long time to pulse is inherently much brighter than one that pulses quickly. This was a monumental revelation. If you know how bright a star truly is, and you measure how dim it appears from Earth, you can calculate its distance. The Cepheid variable became the first truly reliable cosmic yardstick, a standard candle that would allow astronomers to measure distances across the vast gulfs of interstellar space. This tool fell into the hands of Harlow Shapley, who used it in the 1910s to launch a new assault on the question of our galactic place. Shapley studied globular clusters, dense, spherical swarms of hundreds of thousands of stars that orbit the galactic center. He reasoned that these clusters must be distributed around the true gravitational heart of the Milky Way. By using Cepheid variables within these clusters to determine their distances, he made a startling discovery. The Sun was not at the center of this great system. Instead, we were located in the galactic suburbs, about 26,000 light-years from the core. Shapley had correctly moved us from a privileged central location to a more provincial outpost, though he still vastly overestimated the size of the Milky Way and held onto the incorrect belief that it constituted the entire universe, a notion that would soon be overturned by Hubble's work on other galaxies. The final, detailed portrait of our galaxy required us to see through the dust that had confounded Herschel. We needed a new sense, one that could peer through the cosmic smog. That sense was radio astronomy. In the 20th century, astronomers realized that hydrogen, the most abundant element in the universe, emits a faint but specific radio signal at a wavelength of 21 centimeters. This radio light can travel unimpeded through the dust clouds that block visible light. By tuning our radio telescopes to this frequency, we could essentially map the distribution of hydrogen gas throughout the Milky Way, tracing the spiral arms where gas is concentrated and new stars are born. This radio mapping, combined with infrared observations that also pierce the dust, has given us our modern understanding. We now know the Milky Way is a magnificent barred spiral galaxy, a vast pinwheel of stars, gas, and dust spanning about 100,000 light-years. It features a bright central bulge shaped like a peanut or a bar from which two major spiral arms, the Perseus and Scutum Centaurus arms, unwind. Our solar system resides in a smaller, partial spur known as the Orion Cygnus arm, located about halfway between the center and the visible edge. From our quiet suburban vantage point, we look out toward a galaxy teeming with an estimated 200 to 400 billion stars, all orbiting a common center of mass dominated by the supermassive black hole, Sagittarius A star. This grand, swirling structure is not a static monument but a dynamic, rotating system. Our Sun, along with the entire solar system, is traveling at over 500,000 miles per hour, taking about 230 million years to complete a single galactic year. This discovery has been the ultimate exercise in cosmic cartography and humility. We have gone from believing we were at the center of a small, starry disk to understanding that we are temporary residents in one arm of a vast, spinning city of stars, a single thread in a galactic tapestry of unimaginable scale and beauty. While we often think of the solar system in terms of planets and moons, a truly monumental discovery revealed that the Sun's influence extends far beyond the orbits of the most distant worlds, creating a vast protective cocoon that envelops us all. For centuries, astronomers pondered the nature of comets' tails, which always seemed to point away from the Sun, regardless of the comet's direction of travel. The prevailing explanation was some kind of solar radiation pressure, but the true mechanism remained elusive until the mid-20th century. The key insight came from a German physicist named Ludwig Biermann, who was studying the ion tails of comets in the 1950s. He realized that radiation pressure alone couldn't account for the violent and dynamic behavior of these gaseous tails. There had to be a constant streaming flow of charged particles, a solar corpuscular radiation pushing outward from the Sun and shaping the comet's tail like a cosmic windsock. This was the theoretical prediction of what we now call the solar wind. The confirmation arrived just a few years later at the dawn of the space age. In 1959, the Soviet spacecraft Luna 1 became the first human-made object to escape Earth's gravity, and its instruments directly measured this perpetual gale flowing from the Sun. Soon after, NASA Mariner 2 mission en route to Venus provided comprehensive data confirming that the solar wind is a continuous supersonic plasma stream, primarily composed of protons and electrons, blowing at speeds ranging from about 250 to 800 kilometers per second. This isn't a gentle breeze, it's a hurricane of charged particles carrying with it the sun's own magnetic field, stretched out into a spiral pattern by the sun's rotation, much like water spiraling from a rotating lawn sprinkler. This constant outward flow carves out a massive bubble in the local interstellar medium, a region of space we call the heliosphere. Think of the heliosphere as the sun's atmosphere on a galactic scale, a protective magnetic cavity that the entire solar system travels within. The boundary of this bubble isn't a hard shell but a complex series of frontiers where the pressure of the solar wind finally balances against the pressure of the interstellar gas and dust that fills the space between stars. The first major boundary is the termination shock, where the solar wind, still traveling at supersonic speeds, is suddenly slowed, compressed, and heated as it begins to interact with the interstellar medium. Beyond that lies the heliopause, the true outer edge of the heliosphere, where the solar wind is stopped completely and merges with the interstellar environment. The journey to actually reach and cross this boundary became one of the great adventures in space exploration, a task undertaken by the twin Voyager probes. Launched in 1977, these intrepid robotic explorers spent decades racing toward the edge of the sun's influence. In 2004, Voyager 1 crossed the termination shock, and then, in August 2012, it made history by becoming the first human-made object to enter interstellar space, definitively crossing the heliopause. The data it sent back was revelatory. We learned that the heliopause is a dynamic, rippling boundary buffeted by the pressures of the galactic environment. The discovery of the heliosphere fundamentally rewrote our understanding of the sun's role. The sun is not merely a distant source of light and heat. It is an active, dynamic star that constantly blows a protective shield around our planetary system. This shield is our first and most important line of defense against galactic cosmic rays, which are high-energy particles, primarily atomic nuclei, accelerated to nearly the speed of light by distant supernova and other violent cosmic events. These cosmic rays can shred delicate DNA and pose a significant radiation hazard to life and to spacecraft electronics. The heliosphere's magnetic field acts as a powerful deflector, bending the paths of most of these incoming charged particles and significantly reducing the radiation dose we receive here on Earth. Without this vast, invisible bubble, the flux of cosmic radiation bombarding our planet would be immensely higher, potentially altering the course of life's evolution. This discovery connects the most local object in our sky, our sun, to the grandest galactic processes, showing that our star actively participates in a continuous dialogue with the galaxy, carving out a safe haven for us as we journey through the Milky Way. But for all the violence and grandeur of the cosmos, one of the most transformative discoveries hits much closer to home, fundamentally reshaping a question that has haunted humanity for generations: are we alone? For centuries, Mars was the world of fantasy, the red planet of H.G. Wells' war machines and Percival Lowell's imagined canals, a place we projected our hopes and fears onto. The first close-up images from Mariner 4 in the 1960s seemed to dash those dreams, revealing a dry, cratered, and seemingly dead landscape, a moon-like world frozen in time. But as our robotic explorers grew more sophisticated, a new and far more compelling picture began to emerge, one defined not by absence but by the tantalizing presence of water. The first major clues were geological, seen from orbit. Spacecraft like NASA Mariner 9 and later the Mars Global Surveyor revealed landscapes that were hauntingly familiar. They showed vast, dried-up river valleys with intricate, branching tributaries, enormous canyons that dwarfed the Grand Canyon, and the unmistakable shorelines of ancient lakes. Here was undeniable evidence that Mars had a past radically different from its present. Billions of years ago, it was a world with a thicker atmosphere, warmer temperatures, and liquid water flowing freely across its surface, pooling in lakes and perhaps even shaping a northern ocean. This realization was a paradigm shift. Mars was no longer just a dry, dead rock. It was a world with a complex hydrological history, a planet that had once possessed the most fundamental ingredient for life as we know it. The search then evolved from proving Mars had a wet past to asking a more urgent question. Where did all that water go? The answer revealed a world that is still dynamically active today. While most of Mars's ancient water was lost to space as its atmosphere thinned, a significant amount remains locked away as water ice. Orbiters like NASA's Mars Odyssey used gamma-ray spectrometers to detect vast reservoirs of hydrogen, a key component of water, just beneath the surface in the polar regions and mid-latitudes. We've even seen stunning images from landers of water ice exposed in fresh crater impacts and clinging to shaded slopes. Then came the stunning evidence of potentially modern water activity. In 2011, scientists analyzing images from the Mars Reconnaissance Orbiter announced the discovery of recurring slope lineae, dark, narrow streaks that appear on steep, warm slopes during the Martian summer and fade away in the winter. The leading hypothesis was that these features were caused by the seasonal flow of briny water. Salt water, or brine, has a much lower freezing point than pure water, allowing it to remain liquid in the frigid Martian temperatures, seeping to the surface and leaving behind the dark streaks as it evaporated. While recent studies have suggested other mechanisms like flowing sand, the possibility of transient liquid water on the surface of Mars today ignited the scientific community. This cascade of evidence, from ancient riverbeds to modern subsurface ice, has fundamentally recast Mars in our cosmic search. It has transformed the red planet from a geological curiosity into the prime candidate for finding evidence of extraterrestrial life. The strategy has become follow the water, and our rovers are the field geologists on this epic quest. NASA twin rovers Spirit and Opportunity landed in 2004 and immediately confirmed the past presence of water by finding minerals like hematite and jarosite that only form in wet environments. But it was Curiosity landing in Gale Crater in 2012 that truly changed the game. This car-sized laboratory didn't just find evidence of water. It discovered that its landing site was once the site of a vast, long-lived lakebed with water that was not only present but was fresh, neutral in pH, and contained the key chemical building blocks of life: carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus. Curiosity established that Mars had, for millions of years, all the necessary conditions for habitability. The question shifted from was Mars habitable to did life ever actually take hold there? This is the central mission of the Perseverance rover, which is now actively drilling core samples from the dried-up river delta of Jezero Crater, a location perfectly suited for preserving the fossilized remnants of ancient microbial life. These carefully selected samples are being cached for a future mission to return to Earth, where scientists in advanced labs can search for biosignatures with instruments far more sensitive than anything we can send on a rover. The discovery of water on Mars has given us a tangible, reachable goal in the search for life. It has taught us that a planet does not need to remain eternally habitable to be a promising target. It only needs to have had a window of opportunity, a chapter in its history where the conditions were right. Mars had that chapter, and we are now turning the pages, looking for the faintest inkling that we are not the only story ever written in the cosmos. Now, with a timeline stretching back billions of years, we arrive at a question that has echoed through human history: just how old is the universe? For most of our existence, this was a matter of pure speculation and mythology. It's only in the last few decades that we've been able to answer it with a specific, evidence-backed number: approximately 13.8 billion years. Pinpointing this age is not just about slapping a date on the Big Bang. It provides the ultimate chronological framework for the entire cosmic story, from the first spark of existence to the formation of our own planet. The quest to find this number involved two brilliant, independent lines of investigation that converged on the same stunning answer. The first path takes us back to the work of Edwin Hubble and the expansion of the universe itself. By measuring both the distance to galaxies and their redshift, Hubble was able to calculate the rate of this expansion, a value now known as the Hubble constant. Think of it like this: if you see a car speeding away from you and you know both its current distance and its speed, you can rewind the tape to figure out when it must have started its journey. In the same way, by measuring how fast galaxies are receding from us today, we can theoretically rewind the cosmic expansion to find the moment when everything was compressed into a single point, the moment of the Big Bang. The inverse of the Hubble constant gives you the age of the universe. It sounds straightforward, but for most of the 20th century, the measurements were frustratingly imprecise, leading to estimates that swung wildly, sometimes even suggesting a universe younger than the oldest stars we could see, an obvious impossibility. This cosmic embarrassment drove astronomers to refine their methods with relentless precision. The key instrument in this modern effort was the Hubble Space Telescope, which was launched specifically with this goal as a primary mission. Free from the blurring effects of Earth's atmosphere, Hubble could meticulously observe a special class of pulsating stars known as Cepheid variables in distant galaxies. As Henrietta Leavitt discovered, these stars are perfect cosmic yardsticks. By measuring their pulsation periods and apparent brightness, astronomers could nail down their true distances with unprecedented accuracy. Hubble's observations of these stars, combined with measurements of Type Ia supernova, allowed scientists to calibrate the cosmic distance ladder with phenomenal care, eventually arriving at a highly refined value for the Hubble constant. This approach pointed to a universe about 13.8 billion years old. But to have true confidence in such a monumental number, we needed a completely separate, independent test. This is where our second path comes in, one that looks not at the present-day expansion but at the oldest light in existence, the cosmic microwave background. The Planck satellite, with its exquisitely sensitive instruments, mapped the faint ripples in this afterglow with microscopic detail. These ripples are a frozen snapshot of the universe when it was just 380,000 years old. The precise size and distribution of these hot and cold spots act as a cosmic thermometer and a pressure gauge for the infant universe. By analyzing this pattern, cosmologists could determine the exact proportions of the universe's ingredients: ordinary matter, dark matter, and dark energy. These proportions, in turn, dictate how quickly the universe expanded in its early phases. The Planck data allowed scientists to run the cosmic film backward with incredible precision, calculating the time it took for the universe to expand and cool from a state of infinite density to the moment the CMB was released, and then onward to today. The result was a stunningly precise age, 13.8 billion years. The fact that these two completely different methods, one based on the local, modern universe and the other on the ancient, primordial cosmos, arrived at the exact same number is a triumph of scientific cross-checking. It gives us immense confidence that we have truly pieced together the correct timeline. Knowing the universe's age with such certainty transforms it from an abstract concept into a concrete, historical entity. It provides the ultimate chronology. We now know that the first stars ignited when the universe was only a few 100 million years old, a mere infant. Galaxies began to assemble shortly thereafter. Our own solar system didn't form until the universe was about 9 billion years old, meaning we are living in the cosmic equivalent of Middle Age. This timeline places our existence in a breathtaking context. All of human history, from the first civilizations to the present day, is less than a blink of an eye on this 13.8 billion year scale. This number is the bedrock upon which we have built our entire understanding of cosmic evolution, a foundational pillar that allows us to trace the grand narrative from a fiery beginning to the complex, structured universe we see today. Just when we thought we understood where planets could form, a discovery emerged from the ashes of a stellar catastrophe that rewrote the rules entirely. In the early 1990s, the hunt for exoplanets was still in its infancy. No planets had yet been found around Sun-like stars. It was against this backdrop that radio astronomer Alexander Wolskson made an announcement that seemed to defy all logic. He was studying a millisecond pulsar, the rapidly spinning corpse of a massive star located about 2,300 light-years away in the constellation Virgo. Designated PSRB 1257+12, this pulsar emitted its radio pulses with metronomic precision. Yet, Wolskson detected tiny but perfectly regular variations in the timing of these pulses. The intervals between pulses were not constant. They would sometimes arrive slightly early and other times slightly late. After meticulously ruling out every other possible source of error, he reached an inescapable and stunning conclusion. The pulsar was being gently tugged back and forth by the gravitational influence of not one, but at least two small, orbiting worlds. He had discovered the very first confirmed exoplanets in history, but they weren't orbiting a normal star. They were circling a cosmic zombie, a pulsar, one of the most hostile environments imaginable. This finding was as shocking as it was revolutionary. A pulsar is the remnant of a supernova explosion, a blast so violent that it should have utterly vaporized any planetary system that once existed around the original star. The very existence of these pulsar planets presented astrophysicists with a profound puzzle. How could any world survive such an apocalypse? The answer isn't that they survived, but that they were likely born from the destruction itself. Theorists now believe there are two main ways these bizarre systems can form. The first scenario is a story of cosmic resurrection. When the original massive star went supernova, its outer layers were blasted into space, but its core collapsed into a neutron star. If the explosion was slightly off-center, it could have given the newborn pulsar a powerful kick, sending it hurtling through space. This pulsar might then encounter a companion star, ripping material away from it through its immense gravity. This stolen gas would form a swirling disk of debris around the pulsar, a second-generation protoplanetary disk. Within this disk of stellar ashes, dust grains could coalesce, and new planets could form from the wreckage of the old system, a phoenix rising from the cosmic flames. The second possibility is even more dramatic, involving a kind of stellar cannibalism. A pulsar in a binary system could potentially strip its companion star down to its core, destroying it and creating a disk of pulverized material from which new planets could eventually assemble. In both cases, the pulsar planets we see today are not the original children of the star, but a second generation, forged in the aftermath of a stellar holocaust. The environment these planets call home is a realm of almost unimaginable extremity. They are bathed not in the warm, nurturing light of a sun, but in a relentless hail of deadly radiation. The pulsar's powerful magnetic fields funnel intense beams of X-rays and gamma rays that sweep through the system like a lighthouse of death, sterilizing the surfaces of these worlds many times over. Any atmosphere would be swiftly stripped away by the pulsar wind, a hurricane of high-energy particles. The planets themselves, designated PSRB 1257+12b, C, and later D, are unlike anything in our solar system. They are thought to be terrestrial in nature, with masses several times that of Earth, but they are likely composed of exotic materials. With their rocky crusts long since vaporized, they may be rich in incredibly dense elements like carbon, crystallized into structures like diamond. Imagine a world that is, in essence, a gigantic cosmic jewel, orbiting a spinning tombstone that ticks with impossible precision. The significance of this discovery cannot be overstated. Before Wolfson's find, our only model for planet formation was the relatively calm, steady process we believe occurred in our own solar nebula. The pulsar planets proved that planet formation is an incredibly robust and universal process. It can happen not just in the serene nurseries around young stars, but also in the chaotic, radioactive wreckage left behind by stellar death. It showed that the ingredients and conditions needed to build planets are so fundamental that they can emerge even from the most violent and unlikely circumstances. This opened up a vast new parameter space for potential planetary systems. If planets can form around pulsars, they can form almost anywhere. This finding fundamentally expanded our definition of a habitable environment. While it's virtually impossible that life could exist on the surfaces of these particular worlds, their existence hints at the incredible tenacity of planetary formation. It suggests that even in the most hostile corners of the galaxy, worlds can persist, orbiting their dead stars as eternal monuments to the dynamic and creative, yet destructive, forces that shape our universe. This first detection of exoplanets was a powerful lesson in cosmic humility, revealing that the universe's imagination for creating worlds far exceeds our own. For centuries, our maps of the cosmos were limited to pinpointing individual stars and later, the faint smudges of distant galaxies, scattered like isolated islands in a vast, dark sea. But what if those islands weren't truly isolated? What if they were connected, part of a grand architecture so immense that its true form was hidden from us by our limited perspective? The discovery of this architecture, known as the cosmic web, completely reshaped our understanding of the universe's structure. It revealed a cosmos that is not randomly sprinkled with galaxies, but one that is meticulously organized on the very largest scales, a breathtaking tapestry woven together by the invisible hand of gravity and dark matter. The journey to map this structure began not with a single eureka moment, but with the patient, painstaking work of generations of astronomers conducting massive surveys of the night sky. These weren't simple star counts, they were cosmic censuses on an epic scale. The key tool, once again, was redshift. By measuring the redshift of thousands and then millions of galaxies, astronomers could determine not only their distance from us but also their three-dimensional position in space. When they began plotting these positions, a stunning pattern started to emerge from the noise. Galaxies were not spread evenly. Instead, they were arranged in a complex network of dense clusters, long, thread-like filaments, and vast, sheet-like walls, all separated by unimaginably enormous, nearly empty voids. This is the cosmic web. It's a structure that resembles a neural network or the frothy, interconnected filaments of a soap bubble bath, but on a scale so vast it defies human intuition. The filaments can stretch for hundreds of millions of light years, with majestic chains of thousands of galaxies flowing along them like luminous pearls on a cosmic string. These filaments connect at dense nodes, which are the massive galaxy clusters, the bustling metropolises of the universe, each containing hundreds or even thousands of individual galaxies. And between this luminous architecture lie the voids. These are not just empty patches, they are cosmic deserts, regions of space that are profoundly, almost perfectly, empty, spanning hundreds of millions of light years across and containing very few, if any, bright galaxies. To grasp the scale, if our Milky Way were located in the center of one of these voids, our night sky would be almost completely black, with no nearby galaxies visible to the naked eye. The discovery of this intricate web was the ultimate confirmation of a key prediction of the Big Bang model, specifically the version that includes cosmic inflation and dark matter. Recall those tiny quantum fluctuations in the primordial universe, the ones imprinted on the cosmic microwave background. These minute ripples in density were the seeds for everything. Over billions of years, gravity got to work on these seeds. The slightly denser regions had a bit more gravitational pull, so they began to attract more and more matter from their surroundings. Think of it like water draining across a vast landscape. It flows from the high points into the valleys and rivers. In the cosmic context, the dark matter formed the underlying gravitational topography, the unseen skeleton of the cosmos. Because it doesn't interact with light and only feels gravity, dark matter collapsed first into a wispy network of filaments and halos, long before the ordinary matter could catch up. The ordinary matter, the gas made of atoms, was then pulled by gravity into these pre-existing dark matter scaffolds. Once the gas was dense enough inside these dark matter wells, it could cool, fragment, and finally collapse to form the galaxies and stars that we actually see. The glowing galaxies we map in our surveys are therefore just the visible traces, the glittering lights outlining the hidden, massive framework of dark matter. This explanation ties the entire cosmic story together in a profoundly beautiful way. The pattern of the cosmic microwave background from 13.8 billion years ago directly predicts the pattern of the cosmic web we see today. The statistical distribution of the hot and cold spots on that ancient sky perfectly matches the distribution of galaxies and voids in the modern universe. It's a direct lineage connecting the first whisper of structure to the grand architecture we now observe. This discovery was made possible by ambitious projects like the Sloan Digital Sky Survey, which methodically mapped the positions of over 1 million galaxies, and continues with even more powerful endeavors like the Dark Energy Spectroscopic Instrument, or DESI, which aims to create a three-dimensional map of tens of millions of galaxies and quasars. Each new, deeper map reinforces the same breathtaking picture, revealing a universe that is both elegantly structured and born from random quantum chaos, a cosmic web that stands as the largest and most magnificent structure we can possibly comprehend. Yet, for all the grand cosmic structures and distant stellar explosions, sometimes the most profound revolutions in understanding are triggered by observations right in our own celestial backyard. This brings us to a pivotal moment at the dawn of the 17th century, a discovery made not with a billion-dollar satellite, but with a simple, handcrafted telescope pointed at the largest planet in our solar system. In January 1610, the Italian astronomer Galileo Galilei turned his new 20-powered spyglass toward Jupiter and noticed something extraordinary. Lining up next to the bright disk of the planet were 3 small, bright stars. Curious, he looked again the following night. To his surprise, the little stars had moved. They weren't just drifting as a background field, they had clearly shifted their positions relative to Jupiter. Night after night, he continued his vigil, and soon he saw 4 such points of light dancing around the planet, sometimes disappearing behind it or in front of it. He correctly deduced that these were not stars at all, but 4 moons in orbit around Jupiter itself. We know them today as the Galilean moons, Io, Europa, Ganymede, and Callisto. This might seem like a simple observation, but its implications were earth-shattering, quite literally. At the time, the dominant view of the cosmos, supported by the Catholic Church and centuries of Aristotelian philosophy, was the geocentric model. In this model, the Earth sat motionless at the center of the universe, and everything else, the sun, the moon, the planets, and all the stars revolved around us in a series of perfect crystalline spheres. Galileo's observation of Jupiter's moons provided the first direct, observable proof that this was wrong. Here was a clear case of celestial bodies orbiting something other than the Earth. If moons could circle Jupiter, then the Earth was not the sole center of all motion. This single finding delivered a devastating blow to the geocentric worldview and provided powerful, tangible evidence for the Copernican model, which placed the sun at the center. It demonstrated that the heavens were far more complex and dynamic than previously imagined, a place where other worlds could have their own families, their own miniature solar systems. This fundamentally altered humanity's philosophical standing. We were demoted from the center of creation to just one planet among others, orbiting a star that was itself one of countless many. The discovery ignited a scientific revolution but also a personal crisis for Galileo, whose support for this heliocentric model led to his famous trial and house arrest by the Roman Inquisition. His moons were a testament to the power of observational evidence over philosophical dogma. Today, we know those 4 moons are just the beginning of a sprawling royal family. Galileo's 4 are the largest, but as our telescopes grew more powerful, we kept finding more. The count has skyrocketed from 4 to over 90, making Jupiter the king of moons in our solar system, a title it briefly ceded to Saturn before reclaiming it in recent years. This ever-growing number isn't just a statistic, it's a window into the violent and dynamic history of the Jovian system. Many of these smaller moons are captured objects, asteroids or cometary nuclei that wandered too close to the giant planet's immense gravitational field and were pulled into orbit sometimes billions of years ago. They orbit in distant, eccentric, and often retrograde paths, moving in the opposite direction of Jupiter's rotation, which is a clear signature of their captured origin. These moons are often lumpy and irregular cosmic potatoes that bear the scars of a long and violent history. Their orbits are chaotic, frequently crossing paths and leading to spectacular collisions that create families of fragments, all continuing their dance around the gas giant. This constant gravitational jostling reveals a system that is still evolving, a celestial traffic circle where the rules of motion are dictated by the overwhelming gravity of the central planet. But the true marvels remain Galileo's original 4, each of which has been transformed by modern spacecraft from a point of light into a unique, fascinating world. The Voyager and Galileo missions, in particular, revealed that these are not mere inert lumps of rock and ice, but some of the most geologically active and potentially habitable places in the entire solar system. Starting from the innermost, Io is a world of fire and brimstone, the most volcanically active body we know. Its surface is a grotesque and beautiful tapestry of yellows, oranges, and reds colored by various forms of sulfur. Constantly being squeezed and stretched by the gravitational tug of war between Jupiter and the other large moons, Io's interior is heated to a molten state through tidal friction. This results in hundreds of active volcanoes that continually resurface the moon, spewing plumes of sulfur hundreds of kilometers into its tenuous atmosphere. It is a literal hellscape, a testament to the raw power of orbital dynamics. Next out is Europa, a world that presents the complete opposite picture. Its surface is a smooth, bright shell of water ice, crisscrossed by a complex network of dark, rusty-looking cracks. Beneath this frozen crust, however, the evidence strongly points to a global, salty ocean containing more than twice the liquid water of all Earth's oceans combined. This subsurface sea is kept liquid by the same tidal heating that torments Io, though to a lesser extent. The combination of liquid water, a rocky seafloor that could provide essential chemical nutrients, and a source of internal heat makes Europa one of the top candidates in our entire search for life beyond Earth. The thought of what might be swimming in those dark, abyssal waters is one of the most compelling questions in modern planetary science. The largest moon in the entire solar system, Ganymede, is even bigger than the planet Mercury. It's a complex world with a puzzling past. Its surface is a strange mixture of 2 very different types of terrain: dark, ancient, and heavily cratered regions, and lighter, younger areas marked by extensive grooves and ridges. This suggests that Ganymede has experienced significant geological activity, possibly including tectonic shifts of its icy crust. Most remarkably, the Galileo spacecraft discovered that Ganymede has its own intrinsic magnetic field, something no other moon is known to possess. This implies it has a molten, metallic core that is still churning away, generating a magnetic bubble within the vast magnetic field of Jupiter itself. This finding rewrote our understanding of what a moon could be. Ganymede isn't just a satellite, it's a differentiated planetary body in its own right. Finally, the outermost of the four, Callisto, is the most heavily cratered object we have ever seen. Its surface is an ancient record of the solar system's violent early history, essentially frozen in time for 4 billion years. Unlike its internally active siblings, Callisto appears to be largely geologically dead. However, data suggests it too may harbor a subsurface ocean, though one locked deeper beneath a much thicker icy shell. The stark contrast between these four sibling worlds, all formed from the same circumjovian disk of material, yet evolving into such dramatically different entities, teaches us a fundamental lesson about planetary science. It shows how factors like distance from the parent planet, which dictates the strength of tidal heating, and internal composition can lead to wildly divergent evolutionary paths. The Galilean moons are a perfect laboratory for understanding how worlds are made and how conditions for habitability can arise in the most unexpected places. From a revolutionary glimpse through a primitive telescope to a focal point in the search for alien life, the moons of Jupiter continue to challenge our assumptions and expand our understanding of what is possible in our cosmic neighborhood. Those tiny temperature variations in the cosmic microwave background, the anisotropies we glimpsed with the COBE satellite, are far more than just statistical noise. They are the universe's genetic code, a detailed imprint of its initial conditions that has allowed us to decode its composition, shape, and ultimate destiny with stunning precision. Think of the CMB not as a uniform, warm blanket, but as a canvas painted with the faintest of brushstrokes, where regions just millionths of a degree warmer or cooler than average hold the entire secret to cosmic structure. The European Space Agency's Planck satellite, launched in 2009, was our ultimate microscope for studying this canvas. It didn't just see the brushstrokes, it measured the exact shade, texture, and distribution of every single one, turning a low-resolution impressionist painting into a hyper-realistic, high-definition portrait of the infant universe. So, what created these all-important fluctuations? The story goes back to the era of cosmic inflation, that unimaginably rapid expansion in the first fraction of a second. At the quantum level, the inflatoned field driving this expansion was subject to tiny, inherent jitters, random fluctuations in energy density. As the universe inflated at a staggering rate, these microscopic quantum ripples were stretched to astronomical sizes, frozen into the fabric of space-time as minute differences in the density of matter and energy. They became the gravitational seeds for everything. Slightly denser regions had a bit more gravitational pull, acting as traps for the primordial soup of particles. Over hundreds of millions of years, these overdense spots slowly drew in more and more dark matter and gas, growing like snowballs rolling down a hill, eventually collapsing under their own gravity to form the first stars, galaxies, and the vast cosmic web of filaments and clusters we see today. The pattern Planck observed is a direct snapshot of this seeding process, a moment frozen in time when the universe was just 380,000 years old. By analyzing the precise statistical properties of these hot and cold spots, their size, their distribution, how they cluster together, cosmologists could perform what amounts to a cosmic blood test. The results gave us the most accurate inventory of the universe ever compiled. The geometry of the cosmos, for instance, was definitively answered. Einstein's theory tells us that the density of matter and energy determines the curvature of space-time, whether it is positively curved like a sphere, negatively curved like a saddle, or flat like a sheet of paper. The pattern of the CMB fluctuations revealed the answer with absolute clarity. Our universe is geometrically flat. This flatness, in turn, was the final, crucial piece of evidence confirming the existence of dark energy. The total amount of normal matter and dark matter alone is only about 32% of what is needed to create a flat universe. The remaining 68% had to be in the form of this mysterious repulsive energy, a finding that perfectly corroborated the supernova observations and cemented our current standard model of cosmology. Planck's data allowed us to put numbers on the cosmos with razor-sharp accuracy. We now know the universe is 13.8 billion years old, with an uncertainty of just a few tens of millions of years. We know that the atoms making up stars, planets, and us constitute a mere 4.9% of the total cosmic budget. Dark matter makes up 26.8%, and dark energy accounts for the remaining 68.3%. These aren't rough estimates, they are figures etched into the subtle patterns of the CMB, a cosmic barcode we have learned to scan with phenomenal skill. This ancient light is therefore the most authoritative document we possess, a fossil that not only confirms our origin story, but also provides the detailed blueprint from which every galaxy, every star, and every planet was ultimately constructed. And then, after decades of inferring their presence through their violent effects on surrounding matter, we finally saw one. On April 10, 2019, the Event Horizon Telescope collaboration unveiled an image that instantly became an icon of modern science, a fiery, asymmetric ring of light encircling a central region of profound darkness. This was the supermassive black hole at the heart of the galaxy Messier 87, a behemoth weighing 6.5 billion times more than our Sun, and its direct portrait represented a staggering technological and scientific triumph. But what does this image actually show? You are not looking at the black hole itself, as no light can escape from within its event horizon. Instead, you are witnessing its shadow, the black hole's gravitational grip warping the very space around it into a perfect trap for light. The bright ring is the photon sphere, a region where gravity is so intense that photons, the particles of light, are forced into unstable orbits. Some of these light particles manage to escape after looping around the black hole, and it is this escaping light, bent and lensed by the extreme curvature of spacetime, that forms the brilliant, lopsided halo we see. The darkness at the center is the shadow of the event horizon, a silhouette 2.5 times larger than the actual point of no return, created because any light ray that ventures too close is captured forever. This fiery donut of light is a perfect visual confirmation of Einstein's general theory of relativity, precisely matching computer simulations of how a black hole's immense gravity should distort its glowing, superheated accretion disk. Capturing this image was a feat that boggled the mind. A single telescope, even one in space, would be utterly incapable of resolving something so small on the sky. From 55 million light-years away, the black hole's shadow appears about the same size in our sky as a donut on the surface of the Moon. To see it required a telescope with a lens as big as the entire Earth. The Event Horizon Telescope, or EHT, achieved this by linking 8 powerful radio observatories across the globe. From the high peaks of Hawaii and the Atacama Desert in Chile to the volcanoes of Mexico and the frigid landscape of the South Pole. These facilities, working in perfect synchrony, functioned as one Earth-sized virtual dish. They observed the black hole simultaneously over several nights in April 2017, each site recording the faint radio whispers from the edge of the abyss onto stacks of high-performance hard drives. These petabytes of data were so vast they had to be physically shipped to central processing centers in Massachusetts and Germany, where supercomputers carefully compared the signals, a process known as very long baseline interferometry, to painstakingly reconstruct the image. It was a global collaboration involving over 200 researchers, a testament to what humanity can achieve when we unite in the pursuit of fundamental knowledge. The result was more than just a spectacular picture. It was a direct measurement of the black hole's properties. The size and shape of the shadow allowed scientists to precisely calculate the black hole's mass, confirming earlier estimates. The lopsided brightness of the ring, brighter on one side, is a direct result of the Doppler effect and something called relativistic beaming. The material in the accretion disk is swirling around the black hole at nearly the speed of light. The side of the disk that is rotating toward us has its light boosted and appears brighter, while the side moving away from us has its light dimmed. This asymmetry is a vivid, real-world demonstration of the extreme velocities and relativistic effects at play just outside the event horizon. Beyond confirming what we already suspected, the image has opened up new avenues for testing the very laws of physics. It allows us to probe gravity in its most extreme regime, a place where Einstein's theory can be pushed to its limits. So far, general relativity has passed this test with flying colors. The observed shadow is perfectly consistent with the predictions for a Kerr black hole, one that is spinning. Any significant deviation from the predicted shape could have hinted at new physics, perhaps a need to modify our understanding of gravity itself. The EHT's work is far from over. Since this first historic image, the collaboration has also released a picture of Sagittarius, a star, the supermassive black hole at the center of our own Milky Way galaxy. While it has a similar ring structure, it presents a very different and more dynamic target, with its brightness changing rapidly as it consumes clumps of infalling gas. Comparing these two giants, the placid, massive monster in M87 and the restless, comparatively smaller one in our galactic center, gives us a richer understanding of how black holes behave and interact with their environments. Future observations, with even more telescopes added to the network, will create sharper movies of these enigmatic objects, allowing us to watch as matter dances and falls into the void in real time. The first image of a black hole's shadow transformed these objects from abstract mathematical concepts and indirect influences into tangible, visual realities. It showed us the silhouette of a region where space-time itself is broken, a one-way door out of our universe, and in doing so, it gave humanity a powerful new tool to explore the final frontier of gravity. And so our journey through 25 cosmic revelations reaches its end, a journey that has taken us from the first fleeting moment of time itself to the very edge of a black hole's abyss. Each discovery we've explored, from the faint whisper of the cosmic microwave background to the violent chirp of colliding black holes, from the invisible scaffolding of dark matter to the phantom force of dark energy, has done something profound. It has systematically peeled back a layer of cosmic mystery, dismantling our ancient assumptions one by one. We began as the center of a small, static creation, and through these findings we have been relocated time and again to a more humble and more magnificent address. We are not the center of the universe, but inhabitants of a rocky world orbiting an average star in the quiet suburbs of a vast spiral galaxy, which is itself just one glittering thread in a sprawling cosmic web that stretches across billions of light years. The universe is not a serene, eternal stage. It is a dynamic, explosive, and deeply strange arena, born in a fiery beginning, driven by forces we cannot see, and destined for a future we are only beginning to fathom. These discoveries did more than just fill textbooks. They rewired our very perception of reality, teaching us that the cosmos is far wilder, more beautiful, and more complex than our ancestors could have ever dreamed. They answered questions we've asked for millennia, only to reveal even deeper, more thrilling mysteries in their place. What is the true nature of dark matter and dark energy, the twin phantoms that govern the cosmos? Is life a singular miracle on Earth, or is it a cosmic commonplace, perhaps swimming in the hidden oceans of Europa or encoded on some distant exoplanet? What, if anything, came before the Big Bang? The story is far from over. In fact, we are likely on the cusp of revelations even more profound. The James Webb Space Telescope is peering back at the first galaxies being born. New gravitational wave observatories will listen for the faintest ripples from the dawn of time. And here on Earth, physicists are pushing deeper into the quantum realm, seeking a theory that can unite the cosmic and the subatomic. The next chapter of this grand story is being written right now, and it promises to be the most astonishing one yet. Humanity's quest to understand the cosmos is our greatest collective adventure, a testament to our boundless curiosity and our unyielding drive to find our place in the grand scheme of things. So as we look up at the night sky, we no longer see a static painting but a vibrant, living story, and we are both its readers and its authors. We want to hear which of these discoveries reshaped your own perspective the most. Was it the sheer scale of the cosmic web, the haunting reality of black holes, or the possibility of life on other worlds? Let us know in the comments below, and together, let's keep looking up, asking questions, and marveling at the incredible universe we are so fortunate